So welcome. And yeah, so the question about this last week and the calculation things. So I'm kind of leaving this in for those of you who are interested and keen. It's not going to be part of assessment to do calculation. Okay? So you really don't have to worry about it. Now, the question about what it all means, it's actually a bit mind-boggling. That's what it is. Why does the neck have this type of influence? Why does the volume have that type of influence? The only thing I can do is I can direct you to study a bit of electroacoustics. To me, that's the way to kind of get a hold of it, because you have a similar thing in LCR circuits, which is a circuit consisting of a condenser and a coil and a resistance. And they will also resonate, right? So in many ways, what we're doing here is scratching the surface, potentially, blowing your mind with how complex things may get, but we're not necessarily going to go there, right?
Yeah, I just don't really understand there what is the resonant frequency. Like, if you can go back to the slide.
From last week?
No, from this week.
I have the Helmholtz here.
Yeah. So yeah, I understood the equation
Yeah.
approximately.
Yeah.
I mean, like, I didn't understand what is the A really, but
The A is neck cross-sectional area, so it's the surface. Area is surface area.
the surface area
Of the neck.
of
So
the-
this is the neck. So if you have the radius of the neck,
okay.
I think it's 2 pi r or something
Right,
like this.
Yeah.
Yeah?
Okay. And why is the frequency, resonance frequency is about, like, what do I get from it? Like, what is...
Well, that's the mind-boggling thing. It's like, why is the gravity constant this or that? Why is it this or that? It's kind of deep physics.
Okay.
We can't really get into
So it's
that.
not really relevant.
Well, it's relevant to have an idea of this being a fact of life.
Right.
I mean, as I said, what we have, just a second, what we have is a situation whereby you really need to know what is there, what is out there to know, rather than to know the details. Because if
But-
someone, yeah?
The resonance frequency itself, can you explain it?
You have a bottle? You have one there? Can you do this? There's one with a smaller neck up there. Just blow the neck for us and you'll hear the resonance. It should do, because it has to do with volume and the neck. Almost. It's a bit high pitch. How about yours? Any more bottles here? Does yours do it? Well, there you go. Almost happening. You should blow across it.
Yeah, it's hard. but-
Yeah, it's hard, yeah. It's just a basic resonant phenomenon.
Mhm.
That's what happens.
Right.
I mean, in a sense, you have turbulence of air, jet, right? Which is a flat spectral phenomenon. It's noisy, right? If you record it, if you look at the spectrum, it will be fairly flat. And then you're essentially inputting energy, broadband energy, into this system. But the system has resonance. So what system does, and that's actually one of the funny things to grasp and kind of remain precise in articulating this, is that it does not amplify the sound. So very often you will hear even my colleagues say things like, oh, this has amplified the sound, this amplifies sound. Well, technically it does not amplify it, right? It makes it louder where you're sitting, that is the case, but amplification would need an active system.
Will
Okay.
it change the original input as well? Like, its gain or...
Not necessarily. You can have kind of a one-directional energy flow into a resonant system or into an amplifier, so it doesn't have to actually mess with the sound source. Although in real-life situations, you could say that the resonance of the room does mess a very little tiny bit with my vocal folds, but insignificant really.
Right. So, but like now if I'm like blowing it, like there's no one frequency, there is a broad band of frequencies.
Well, there is one resonant frequency, so if you look at the spectrum of this, you will find one peak. You may find some harmonic peaks as well, and you will find the underlying broadband noise. Yeah. So what actually happens is that somehow the broadband energy gets squeezed into the resonant frequency. Okay, so what you would see is that the overall frequency, the energy, sorry, does not increase in the system. But if you compare the blowing without the bottle and the blowing with the bottle, you will see that certain peaks have risen compared to
But
the.
isn't it like there are a lot of different broadbands that they have like, wow, I forgot the term, but the root frequency or something like
Fundamental
snare drum.
frequency, yeah.
Fundamental frequency, like snare drum, for example, right?
Yeah?
So is it the same principle?
No, it's much more complex. The vibrational patterns of a skin, drum skin, a head, are very complex.
Right.
I used to teach this acoustic instruments in the IRI, Instrument Recording Investigation, but I guess Al is doing that now, yeah? Is anyone following Instrument Recording Investigation?
Yeah, we didn't start it yet. So.
Yeah, so he's gonna go into it, and I have slides on this, but he's taken, so that should be made clear at some point. It's much more complex. This is actually a fairly simple resonance system. I mean, it's that simple. Okay? So actually all these exercises are kind of, see if it excites you, if you want to study this, I'm very happy. But actually I've already had some comments on the complexity of stuff, which was not very encouraging. But therefore I will try to, keep it simple, I guess. But, to have the references there, to have the complexity behind available, I think it's crucial. Just make sure you don't get,
Also
frustrated.
For the chapter, it's like 70 pages or something. That's what you meant?
Yeah. Go for it. Yeah. I mean, technically, if you look at the numbers, you're supposed to spend another 4 or 5 hours every week with this subject. I know you don't, and I don't want to, force you to. I probably wouldn't have means to do it anyway. But that's the point. I'm just showing you the vast universe of acoustics, and grab your bits. Remember. Actually, the thing that I prefer to do as well is operate more with anecdotal stories. Did you hear this? That. Those are the things that we remember better.
Yeah.
I mean, if you have some passion for this, then everything sticks. I mean, I remember when I started studying officially digital signal processing, it was, I don't know how it happened, but I knew everything ahead of time without ever having studied it. It kind of happens, when you really love something, you're really interested, everything sticks. All the details just remain there. It's wondrous. So, yeah, I think, but in any case, what I would like to ask you to do is stop me when some things are just totally off the map, okay? Because evidently I'm trying to show the vast universe, but it is for you. So if you are totally mesmerized by some concept or something, stop me and let's discuss that in more detail. I'm happier to spend more time with simple things that are vague rather than actually go through all the complexities that are in the slideshow. Okay? Especially because, in fact, the thing is that I'm still considering the exact content of the assessment. I will talk to my colleagues, see what they think, because I'm not too sure about lecture notes as a thing.
I was about to say, like, I don't know, I guess everybody got a different style for, like taking notes. And
Yeah.
For me, I don't really take notes.
I know, me neither, because I remembered it all. I knew it before it happened.
It's not just I remember, but like, I don't see that, like, if I'll write about it, it will make my, like, understanding of it.
Yeah. Yeah, we'll see. I mean, it's still not very urgent, although the deadline will be in January. We might actually resort to just measurements and some description of this, kind of keep it practical. It just hurts me a little bit because this used to be the only proper academic theoretical subject. To me, it seems that we are overly practical, and practice anyway you learn from practice. And this kind of stuff is the real, academic content, so to speak. So I'm really sad to leave it, but you know, I'd be more sad to frustrate you guys with, you know, unnecessary complexities. Okay, so questions this week, last week. If you're interested, go for it. If you're not, just leave it. But I just don't. Obviously, you know, when I assembled all these slides, it took a while.
Yeah.
So to start deleting things, it would be very painful for me as well. So.
Can you maybe go through the standing wave question?
What is the standing wave question? Is there one here?
Yeah, like if you go back.
You mean from the last week? Do you remember the question?
No, like the second, like last week's lecture, there was a standing wave question. Week 2.
Yeah, yeah. Okay, let's see. Correlation.
Not this one. Like if you go.
Maybe it's from week 1 then.
No. It's there. Like if you go,
At the end.
Yeah, if you continue, here you go. Yeah, past it. No, like back up.
I was there. That's where I started.
No, like more.
More?
More. Go down. Yeah.
Oh, you want so not the question, just the actual.
This thing, like you were asking later.
Mm-hmm.
More down. Yeah, here. Yeah, the boundaries and the nodes and here. Yeah, one up. Yeah, this one.
What is the relationship between wavelength and tube length?
Yeah, I wasn't sure about that one.
Okay, so it's kind of instrument acoustics really. So you're gonna get there. So I'm gonna be really brief because I do want to. We have tons of things for today as well. But the point is that if you have a node, right? A node is the point of minimal excursion at one end of the resonant body, and this is an idealized one-dimensional resonant body. Then, and on the other end, you have an antinode, so you have maximum excursion, right? Then this would be one of the patterns that you observe. The other one would be the one where this is so 3.5 or 1.5, and the other one would be just this one. So here open and here closed, that would be the fundamental resonant mode. So the point is that if you have node antinode at two ends, then the lowest frequency, the resonant frequency, has a relationship with quarter of the length, right? And if both ends were closed or both ends open, it is the same situation. So you have the identical type of termination. Then you would have twice. So you would have half the period in there, right? And if you do the extrapolations here, which is part of instrument acoustics, you will see that actually if you have differing terminations, then you will have the fundamental, the third harmonic, the fifth, the seventh, the ninth. You won't get even harmonics. Whereas if you have identical terminations, then you will have even harmonics as well. Okay, but it's definitely part of instrument acoustics more so than architectural acoustics, so you can expect that. Okay, let's get into the rooms. So today we're going to discuss these 4 main chapters: absorption and reflection, room properties, reverberation, and natural modes. So we're going to essentially look at the technicalities behind enclosures, typically rectangular ones. The practical side of this in terms of control rooms, concert halls, recording rooms will come later. Okay, so we're kind of preparing the soil here just to understand the basics. Okay, so first thing, absorption. This is actually fairly simple if you observe it, but the implications are not always readily available as we consider certain scenarios. Okay, so what we have is 3 intensities, right? We have the incident one, so that's the incoming sound, so to speak. We have here some kind of a boundary. Then we have the reflected intensity. I may refer to it as energy as well. We have the absorbed, which stays in the material, which is converted to heat. And then we have the transmitted energy. Okay? Now, the interesting question here is, how can we decrease the amount of reflected energy?
Like using like more absorbent material?
Yes, that's one. And
The form of material?
so still the material, so that's fiddling with absorbed energy. But the
Angles,
crucial thing is, what is the other option?
Angles?
No, yeah? It's, I can't hear that?
Temperature.
Temperature. Not significant. Not significant, but it's here, there it is, it's just in front of you. So you can increase the transmitted energy, right? So that's the thing that we typically forget about. We always think, okay, we want to have less reflection, so we do something to get more absorption. But actually, we can also increase the amount of transmitted energy, right? So that's my little story about a timber house in the forest, right? Actually, a lot of energy just goes straight out, especially bass frequencies, and it's great, right? If you have a brick wall, then most of the bass will be reflected back, and if you want to absorb it, you really need thick bass straps and all the rest of it, right? So that's why this is crucial, so you always know, okay, if I want to fiddle with one of these, right, I have to consider the others, and all of them, if I really want to be thorough. Okay, so that's this basic of absorption, sound power per unit area. We won't deal with this much. You can do calculations with this, with coefficients. Okay, I'm not really bothered to push this topic. Can you figure out what the coefficients add up to from this equation? No, it's kind of math. If you do, you can feel proud of that. So what we will encounter then, which kind of derives from this without necessarily us going through that, is the absorption coefficient. Okay, so that's one of those things that you can easily look up for different materials. That's the one thing that will have its place in simple equations that you can just quickly use. And the thing to know is that if the absorption coefficient is 0, it means nothing is absorbed. It means you have a perfect reflector. Do we know what would be?
What is it, the absorption?
0.
No,
If-
no, I mean, what is it like? Is it the material?
It is a property of the material, yes.
Right. Okay.
Absorption coefficient of material. So if it's a perfect reflector, it is 0. What would be a perfect reflector? Do we have any?
A mirror?
A mirror.
Yeah.
Well, for the light, but not
something
for sound.
shiny and smooth.
Shiny and smooth, yes. Typically concrete
Concrete,
is very close to
Would mirror be a good sound reflector as well?
mirror.
Yeah, because I read about
No,
that.
it's not. Actually, it's slightly counterintuitive, but Windows glass is actually not as reflective as you would think.
Oh.
So studios that employ a lot of glass aren't that horrible in the end. That's what they say. So you can get away because it actually transmits quite a bit as well. Okay, so it's not just about the surface, it is also about the thickness, right? And it is also about the density behind the surface, right? So there is something about the shiny surface. In fact, the surface waves are quite crucial. If you're interested in this, you can try to look up some discussion on violin lacquer, and you will find that there's people who spend their lives just with violin lacquer study, how it changes the sound, what it does, the thickness of it, this and
What
that.
is it?
Lacquer.
The varnish thing.
Varnish, yeah. So it's like it's kind of a plasticky layer on the wood, right?
The black thing?
Yeah, no, like a see-through paint. Yeah, that you put on the wood.
A bit like paint, yeah.
Oh,
lacquer.
Okay.
Yeah,
okay.
yeah. So there is something to be said about surfaces in terms of transmission. Also, if you think about cymbals, for example, you will see the brilliant finish, the natural finish, raw finish. So you can actually have the same property of the object, but the finish, the surface will make quite a difference. in how the object behaves. Okay, so 0 is a perfect reflector in terms of absorption coefficient. Open window is 1. So you see, that's again what we were trying to kind of install in our minds, is that we can achieve no reflection, not necessarily just by introducing absorption, but by making sure it all just leaves the place. So open window, everything goes out, nothing comes back, there is no reflection. Okay? I mean, it depends what's outside of the window, you know, because typically all environments will give you some reflection. So if you have an open window in the forest, it won't be one, something will come back. But we are now dealing with theoretical things. And just to give you an idea of the absorption coefficient altogether, anechoic chamber is supposed to also be absorption coefficient 1. Okay, so in terms of reflection, one key term that will make you sound very knowledgeable if you talk about this is specular reflection. Okay, specular reflections are essentially what you expect. You could call them normal, everyday reflections. The point is that the incident angle is the same as the reflected angle. That's what we're looking at. So it's the kind of thing that happens on a pool table. If you don't spin the cue ball too much, you get a kind of accuracy of reflection like that. Now, this will depend largely, in our case, on the frequency of the wave. Okay, so the boundary and the surface have to be related to the wavelength in a way. Okay, so if you have high frequencies, smaller boundaries will do it, but you will have to have a very smooth surface. If you have lower frequency waves, right, the surface does not need to be as smooth. So you have a kind of a relationship between size and frequency, as usual, by the way. In acoustics, it's kind of all over the place. Okay? If you want to, I mean, this is a kind of a way of conceiving what's going to happen. You can work with the source, with the image source. You can do a straight line from there. But the point is that in real life situations in acoustics, you don't quite hear it coming from the other side of the wall because of the complexity of reflections altogether. Although it could be an interesting experiment, right? So you could build an experiment whereby you say, okay, I'm going to turn that speaker towards the wall, put a baffle between me and the speaker so I don't get the direct sound. Then it will come off the wall, and then you can, blindfold people and ask them, where does the sound come from? And if they say it comes from behind the wall, then you've kind of proven that it has some sense. But I would consider this to be a stretch. It works very well for light, okay? In sound, it's likely to work well for high frequencies, okay? So that's specular diffraction. Now, the thing that is quite interesting, again, if you're interested in numbers, please have fun with them, is the consideration of path difference when we have a reflection like this. Okay, so the point is that I'm the receiver, this is the source of sound. There is a path length, which is the length related to the direct sound, okay? And there is the path length of this reflection. So what this means is that I will have essentially a repeated waveform, a repeated sound that comes in later. Okay? How did we call this?
Reflections.
No, I'm referring to the fact that the sound is almost identical with some delay in between. Correlation. Okay? So these would be correlated wavefronts with some latency. Okay? And you remember we had different situation if we are summing correlated sources and summing uncorrelated sources. Okay? So if we have correlated sources, what are the two things that can happen? We have interference. Yeah?
It's a dip, yeah.
And what, not necessarily a dip, it could be a dip, but it could also be a peak. Okay, so we have destructive interference and we have constructive interference. Okay, that happens if the sources are correlated. If they're uncorrelated, they don't interfere, right? But because one is the reflection of coming from the same source, these will be correlated. And what we have here in this situation is we can figure out what would be the latency in terms of the reflected sound coming later, right? So in this situation, well, we're not 5 meters off the wall, but you can maybe calculate that with the Pythagoras or something, probably about 4 meters off the wall anyway. And 4 meter distance, it's 17 milliseconds. Now, in terms of having some idea about what these milliseconds mean, what I would suggest is the thing that I typically remember is that the width of your head corresponds to just below 1 millisecond. Okay, so that's a kind of a ballpark thing for me to, you know, as soon as I see some milliseconds and have to think about spatial relationship, that's my kind of go-to reference in that sense. But you can also remember, you know, for example, that, you know, 343 meters per second, right? So how many centimeters is a millisecond? Shall we go in there? Go there? It's early in the morning. Anyway, if you have just basic understanding of what this means, that's plenty, probably.
Can you explain, like, I don't understand what is D2 minus D1?
So this is the difference between directed and reflected sound.
Okay.
D2 is 10 meters, 5 plus 5. D1 is 4 meters, that's your direct sound. It's 6 over 343, you get 17
What
milliseconds.
is the 343? It's like sound?
Speed of sound,
Speed of sound. Okay.
yeah. 343 meters per second.
Is the speed of sound, like in the live sound lecture before, we were talking about how speed of sound can like be affected by like humidity and things like that.
It can, yes. It is affected, but it's not huge. It's just a bit. It's affected by humidity and temperature and the medium. So an interesting thing when you inhale helium, as you do, in order to get a chipmunk voice, you know this phenomenon, right? So actually it is not just the influence, it's actually debated, as far as I understand, but initially everyone thought, well, it has everything to do with how it modulates your vocal folds, but actually it has to do with the fact as well, at least, if not solely, that helium has a different speed of sound transmission. So it is also the fact that your lungs are full of a different type of gas, which will change the pitch because it changes the speed of sound in the medium. But that's just an anecdote. Maybe it's the only thing you will remember. Okay, so what happens then? Because of this path length difference, we get comb filtering. Okay, so there are ways of understanding this, but in essence, if you think, if I have 17 milliseconds delay between reflected and the direct sound, and these 70 milliseconds correspond to half wavelength, right? Then that frequency will be destructively destroyed, muted or attenuated, I should say.
Half wavelength?
Yes, because you need to, if you have if 17 milliseconds is a full wavelength, then you get back into phase. Then you will get a louder sound coming out because you have constructive interference. So for destructive interference, the path length difference has to correspond to half the wavelength. Okay?
So, like, the reflections have to be, like, calculated so that the difference between them and the direct source wave will be half?
I'm not sure I understand the context. They have to be calculated? What are you trying to say?
Halved. Like, they...
Oh, halved.
Yeah.
I'm not sure why. I think I formulated it precisely. I'm not sure. You would have to repeat it again, the full sentence, if you want me
so
to
basically,
correct.
like the reflections, like the delay,
Path length difference, yeah?
the path length difference have to be halved from the direct source, like the path of the source, in
No.
order for it to be like not out of phase, to be in phase.
I'm afraid that the grammatical structure is ambiguous
okay.
of what you're saying.
So yeah, I guess
We would have to sit down and write it down and analyze the logical implications of what you've just said. I'll try to formulate it again very simply. So if the delay corresponds to half the wavelength, then you will get destructive interference.
Right, and the delay is in milliseconds.
Potentially. It holds for light years as well.
Oh.
Obviously in sound in this domain it's a few milliseconds typically.
Okay.
So we could actually try to get an idea what would this frequency be. Okay, it comes later as a calculation example. Would you like to try this? So if we have this situation, we have 17 milliseconds difference. So what would be the frequency at which we will get destructive interference? About, huh? So actually the way I would do this is I would take 34 milliseconds to be the full wavelength, or the period duration, to be very accurate. Okay, and that would give me about 300 hertz, 30 hertz. 300 hertz, 30 hertz? I need 1,000 in the end, so 30 hertz. Yeah? So that's what you would get. Now, the thing is that you get this fundamental frequency attenuated, but you will actually get all the harmonics attenuated as well. Okay, so that's what happens. That's how you get a comp filter. So if you think about this, so if the delay corresponds to half the wavelength, okay, you get the destructive interference. But if it corresponds to 1.5, then you will again get destructive interference. So,
How
yep.
do you get from the doubling the time, milliseconds delay, to the frequency that would be?
Milliseconds.
Yeah, you took the milliseconds and you got to the frequency. I missed this.
Yeah. Actually, obviously, I did my little, cheat in, the way I would quickly figure it out. And it might not be very transparent. I'm sorry. If you want to do the math, here it is. Okay? And it's actually the math that will give you further harmonics as well. Okay? So if you have path difference of 20 centimeters, right? That's what you do. So essentially you have N135, and this is your equation. So you do your meters of path difference here, you do 2 times N over N. Okay? So here what you get is that the wavelengths would be 0.4, 0.13, 0.08. So you see that was my doubling there. So from 0.2 I just jumped to 0.4. Because that if 0.2 is half the period, then 0.4 is the full period.
And so how did you apply that previous example to this equation? I don't understand how the numbers go into this equation.
Well, this is just, equation that you can assume is right. I kind of tried to explain, you understand the principle of destructive interference here, right? So if it is half the wavelength, the amount of delay, then it will destructively interfere, right? So I look at what is the delay, and I'm interested which frequency has a period duration which is half this delay. So I double the delay, right? And then I calculate the corresponding frequency, and that's how I get it. Does that make sense?
Yes.
Okay? And then in this case, what you also see that we will have odd integer multipliers in here. In fact, they will be dividers. So you actually get a series of notches, right? And here, this is period duration, right? So the longest period duration corresponds to the lowest frequency, right? This would be one higher one higher, and so on. And in the end, you get this beautiful comb filter pattern. That's what happens. So we will do a practical with this, probably next week. Okay? Or indeed, we'll see how quickly we go this week, but I guess it will take time just to get friendly with fuzz measure and all the rest of this. Okay? So this is the second half of the equation. So what we have then is a set of period durations, right? And then from that, 343 over a period duration, that's how you get the hertz. You actually get the frequencies. And now you see that the longest period duration is actually the lowest frequency. Okay? So what we have then is for 0.2 meters path length difference, you get these notches. Okay? Kind of makes sense? So for 2 meters, you can just put a comma here. So again, you can kind of get an idea of what to expect. But again, this will all become even more clear probably when we check it. Okay, next one up, we have room consideration. So we looked basically at reflections, what happens at the boundaries. Now we can go a step further and see what happens in a room. I guess everyone is clear with volume of the room, how you calculate this for a rectangular room. It will be useful in many approximations. We will actually deal with approximations only. To do this very accurately is overly complex. In fact, with the best modeling software, there's still quite some limitations. The acoustics in a room are just too complex for computers, pretty much. So we only have approximations there. Now let's look at what happens actually as a source projects a wavefront to the receiver. Okay, so this is a kind of a concert hall looking sketch. There's something on the stage here, and there is someone listening to it up there. And the first thing that happens is direct sound. Okay, it will be the loudest and it will be the earliest wavefront that comes through. Second one will be a set of first order reflections. Okay, so a first order reflection will be one which has a single point of reflection. So if you were to think about how many first order reflections there could be, that's a kind of an interesting brain exercise.
Infinite.
No, first order reflection. So it has to be reflected only once.
How many walls?
Yeah, how many surfaces there are. Now obviously in this room we could say, okay, floor, back wall, side wall, 6 walls, but actually this desk is also a reflective surface. So we would have to have a fully bare, empty room in order to have this accurate.
So in this case, the receiver, you say first order reflections depends on how many walls there are. What about the wall behind them? Because surely there'd be more from the source point in this example reflecting behind them that gets the receiver before any bounce back from behind.
So the first order reflections will arrive at different times, depending on this distance, path difference. The other thing to add is that the reflection from front and back walls will be softer. Partly because I project in one direction and partly because you also listen more in one direction. So if you would do this with probe microphones, put them in your ears, you would probably get a situation where it's significantly softer, the back wall reflection from the side wall. And in this case, we have somewhat absorptive ceiling. These are acoustic panels, right? We'll talk about them due course, but they're supposed to absorb sound. Okay, so that's the first order reflections, and you've guessed it already. Next one up is second order reflections. Okay, I claim that there are 13 total. Any idea why? So if you think about it, what you have is the necessity for 2 points of reflection. That's evident. And then if you think about it, it means that the first reflection has 6 options. There are 6 surfaces it can bounce off of. But the second one has to bounce off of a different surface. Right? So it cannot bounce off the same surface. It's not quite like a ping pong ball. Right? So this means that it's 6 times 5. Right? So for every wall that acts as a first reflection, there can be only 5 other walls that can act as a second point of reflection. So we have 30 second order reflections in a rectangular room. Now this is not even rectangular, but it kind of shows you the complexity of the situation. And what's potentially even more important, it shows you how the points of reflection are spatially distributed. Namely, that there are certain areas where you expect quite a lot of reflections to come through, and there are certain areas where you don't expect any reflections to be happening. So if you want to treat those reflections, right, it kind of makes sense to consider where they are. Okay? Now we will talk about the effect of treating early.
First order
Excuse me?
reflections. I have a question about first
Yes.
order reflections. Why would it be 6 instead of 5, since we are not facing or really?
Well, it still comes. Maybe you don't hear it because it hits
Yeah.
the back of your ear, but it's still a reflection.
But isn't the sound reaching it from reflecting the other surfaces first to the back wall, since I'm not facing it at
It's
all?
coming later, but it's still a first order reflection.
Okay.
So if I have a tunnel, right, I will have many second order reflections coming in earlier than one of the first order reflections.
It's like in an ocean where, like, you know, it's a pulse that is like, it's a circular pulse, right? So it goes back as it goes forward as well, the sound wave.
I'm not sure I get the analogy. Why is the analogy with the ocean interesting?
I mean, like, if, like, you know, when you take a rock, for example, and you put it in
Yeah,
the ocean,
yeah.
so it creates a circle that...
Yeah, you get concentric
so
circles.
this is the type of wave that it is, right? So that's why
Yeah,
it's going to the
yeah. So we kind of talked about this already, whether we consider sound a wavefront or we consider it a ray. Is it an arrow or is it a concentric circle? And the answer is it's none of these. Both are models. Both are things that monkey brains produce in order to approximate the phenomena. And if you are dealing with bass frequencies, the idea of concentric circles is more useful. If you're dealing with high frequencies, the idea of rays and arrows is more useful. Okay? So this evidently, in acoustical modeling software, most of these operate with ray tracing. So this is your ray tracing model. So you actually consider the sound to be an arrow rather than a circular thing. I mean, if you were to draw concentric circles and the reflection of those circles, you wouldn't be able to view this meaningfully at all. Okay, so it's just another, show how at this stage, in this situation, arrows are helpful. Okay, so second order reflections, and what do we have typically? Progressively softer, because you lose energy at the point of reflection. You also lose some energy in transmission. Okay, and further delayed, obviously that has to do with the path length. And then third order reflections. So by now you probably get it. 6 times 5 times 4 gives us about 120 in total. And at this stage, obviously you can't really follow any of these lines unless you are, I don't know, you might do. But we are still only at the third order reflection. So it kind of goes to show the complexity of the situation. And the other thing, again, is you start to see the bunching of reflection points. I mean, I'm not sure how well you can see this in 3D, but it kind of works, no? And then the other thing is that you might understand from this sketch is what happens if I move the source just a little bit. What happens if I move the receiver just a little bit? You can imagine this mesh of lines going totally crazy and realize that, well, actually the interesting thing to realize is that sonically it's not a huge difference, right? If you sit there or if you sit there and plot this graph, it looks very different, but sonically it's not, right? And that's the point, that the reflections fuse perceptually. Right, so this is just to show you the kind of the technical background of it, but you understand that you don't hear these reflections separately, right?
Is it possible that, like in terms of psychoacoustics, that, for example, like if I'm talking to you right now and I'm here, you're there, and then like I'm shifting a little bit, like your brain is basically like kind of fixated on a certain ratio and it's following it.
Well, it's not math, but there is a lot of compensation going on, right? So there is many ways in which certain properties will be excluded from my perception automatically. They will not reach my perception because of my attention window, right? But if I don't care what you're saying, I may actually be able to trace or kind of hear the difference in reverberation as you move around. But if I'm listening to what you're saying, then my attention is just insufficient to cover that as well. Fourth order. Yoo-hoo. And now we are actually slowly getting into what we call a reverberant field. Okay? So how do we plot this more meaningfully? By looking at the impulse response. Now, the impulse response is a huge chapter. It's a very exciting way of analyzing a system. It is a way of analyzing a system which has a complex time characteristic. Okay, because that's what we're doing. We are essentially looking at a direct signal from source to the receiver, and we're looking at all the reflections, and this is your impulse response. So the interesting thing here is, what you will see is that we typically obtain the impulse response with a sine sweep.
With that?
Sine sweep. So we take a sine wave and it goes whoop. That's what we're going to do later today. Okay, and what we will see is the impulse response. So actually there is a translation between the time domain, impulse response is time domain, this is time, and spectral domain, frequency domain, which will be what you're used to see in terms of a flat response or not very flat response in frequency. And if you take a spectral analyzer, typically we use fast Fourier transform, FFT. You've probably seen this, heard this before. You can actually take the FFT of the impulse response and you will get the spectral response. And you can work backwards as well. You can take a spectral response and do the inverse FFT, get a time signal that corresponds to that spectral response. So actually we have a back and forth highway between time domain and spectral domain. Okay. Now, in terms of analysis, I actually don't have many slides on this. There are more robust methods, thing called maximum length sequence. Also, it is a matter of fact that what you can do is you can take, I actually have one in the drawer, I'll probably bring it down for the practical, a clapper, a thing that goes clack. And then you could actually record in time the impulse response of a room or something. I'm not sure we're going to introduce this in the practical, who knows. But what you can also do is use a starter pistol, or you can use a balloon pop, and you will get the impulse response. Okay, so it is actually a time signal. It is the recording of what happens after a single impulse. Now, the issue here with the single impulse is that it is very poor in terms of energy. Okay, so the energy of a signal, anyone knows how can we estimate the energy of a time signal? We look at the surface. Okay, so you have a peak, right, which is your amplitude peak, but amplitude peak is not the energy of the signal, right? So if you have an impulse, what you actually have is infinitesimally short burst of energy. So the surface that you can squeeze in, so to speak, into an impulse is very small. So you need a huge excursion, a very short, huge excursion, to actually get any viable amount of energy into the system. That's one of the reasons why we use a sine sweep. So you can kind of think of it being an impulse spread in time, right? Because an impulse is a flat acoustic phenomenon, right? Spectrally flat. So if I have an impulse, it has bass, it has mids, it has high frequencies, right? You can remember this, what happens if you plug in a cable into an amplifier that is on. It goes cluck, it goes impulse, right? And you hear it. It has highs, mids, and lows. It's spectrally near flat. Okay? So that's the thing that we're doing. We're kind of stretching the impulse in time by its frequency, so to speak. And then we can get the same thing technically as if we did just an actual impulse response.
Is it some kind of a potential energy?
No, it is actual acoustic energy. Okay, so that will be the impulse response. And looking at the impulse response, you should be able to identify, first of all, the direct signal. You can potentially figure out what is the distance between the source and the receiver, which should correspond to this amount of time, if this is well aligned. And you can also estimate the duration of time between the first reflection and the direct signal. And you understand if you're in a large room and the source and receiver are not very near any of the walls, this can be significant. And psychoacoustically, it is one of the clues in terms of the size of the room. Okay, so if you take an artificial reverb and it has a room size parameter, what you're doing is increasing this delay. Sometimes they call it pre-delay as well. Okay, and then typically on an impulse response, you will see quite a few reflections that come in first. We call them early reflection. You typically see them apart. This is a sketch where they start to merge only later, but it obviously depends on the resolution. Okay, now in terms of the limit between early reflections and late reflections, there's many different ways of approaching this. Typically in acoustics, we have distinction between speech situations and music situations. And for speech, we consider it 50 milliseconds, for music, 80 milliseconds. Just so you have a ballpark value to relate to. Okay, so the point is that in the previous impulse response will not be perceived as repetition of the sound. It will be perceived as reverberation. You would actually need to mute a part of it, right, to get a jump, and then you could perceive it as echo. Okay, and it's actually quite interesting. So if you think about it, if you have I'm not sure about APDI recently, but about the depth of filter studying that you've done. But maybe you remember or understand already, or somehow know, that if I delay a digital signal by one sample and add it back to the original, what do I get?
An echo.
No. I get a low-pass filter. Okay? So just delaying the digital signal by one sample, adding it back to the original, I get a low-pass filter. If I increase the delay time from one sample, which is the shortest possible delay in a digital system, if I increase this delay time, then I'm going to start to get comb filters. In fact, the amount of samples will correspond to the amount of notches. Okay, so as I push it further, I get a comb filter. And then at some point, I will actually start to get some kind of spatial effect. Okay, so in manipulating the time of a signal, the shortest durations will give you filtering. Medium durations will give you a sense of altering the spatial properties. And only then you will get an actual perception of repetition. Right? So all of this is repetition, but the times are so short that we cannot perceive these things as repetitions. We perceive them as a reverb characteristic. You have to remove quite a lot of this, says larger than 35 milliseconds, for this to be an echo. Otherwise, it's plain reverb. Okay? So that's the kind of microscopic scale of things in this domain that should, well, I mean, it's intuitively not horribly counterintuitive, I would think. Okay, so technically about reverberation time, we typically call the reverberation time the duration of time it takes for energy to drop, intense level, I should say, sound pressure level to drop 60 dB. Okay, so the thing is that when we have a few basic approximations, Sabine equation, Eyring equation, we're not necessarily gonna look into this. It's not horribly accurate, but it's a good ballpark if you wanna predict the reverberation time of a room. Typically what we will do is we will measure T30. So essentially the reverberation time is typically your capital T, and then subscript will contain the amount of decibels you're looking at in terms of dropping. So T60 is the duration after which level drops 60 dB. T30 is duration after which it drops 30 dB. The reason why we typically we can directly measure T30, it has everything to do with the levels. Okay, so the noise floor in the room, if you consider it maybe around 40, 50 dB, right? That means you have to kind of be above it, so you can maybe measure until 60, which means you would have to push in 120 dB into the room to get your reverberation time like that, and that's a bit over the top. So typically we do just with 30 dB and double that. But that's actually not exhaustive because it's not necessarily linear, the reverb decay in a room. In fact, we will talk about this later on. When is it bulging? When is it kind of hollowing down? So it's not necessarily something that you can directly predict or directly multiply like that. So theoretically, if you simplify things, sure, T60 is double T30, but in practice it is not. Okay, so briefly, just for your reference, here is Sabine's formula, which shouldn't be horribly complex because volume of the room is fairly straightforward, right? The 3 dimensions multiplied. A will be your absorption surface. So you have to calculate and sum all the wall surfaces, then you get the A, and you get the absorption coefficient somewhere in the game as well. Okay, that's your, in this A, it will be alpha times S and sum of all the surfaces and their absorption coefficients. So it's a kind of the basic approximation. It kind of makes sense. You look at the volume, you look at the size of the surfaces and the property of the surfaces, put it in there, and it kind of gives you an approximation of reverb time. I mean, it was one of the early, how should I put it, holy grails in acoustics. How to approximate this? Is there an equation? I'm not sure it's so popular anymore. You know, since we can measure rooms. In fact, I should never say measure rooms because we can't measure a room, right? It's too complex. We can only measure a source-receiver situation within a room, right? But in any case, we have much more complex measurements and models. So this kind of fascination with reverberation time is kind of over. But nevertheless, there it is for your reference. Approximately how it could work. Here's an example: carpeted floor, masonry walls, grid, ceiling, times, plus, times, in the end 0.89 seconds. It's not very fascinating, I think. So we can get on to the last chapter for today, which will be what goes on in a room, and this will actually relate back to what we have seen in one-dimensional resonances. Okay? So what we consider then is that there can be, if you have parallel walls, you will actually have a one-dimensional resonator between those parallel walls. So essentially it will resonate, just like a string will. The air between two parallel walls will resonate. So this set of resonances that have to do with two parallel walls are what we call axial modes, okay, in the room. And these are actually fairly simple to calculate because it is the same old business. You have a distance, right? You have a speed of sound. You have the index of your resonance. So if you start with 1, you're going to get the fundamental, and then you get higher frequencies as well. And then you have the F for frequency, and then you will figure this out. Obviously, if you want to calculate frequency, then your variable is distance between two parallel walls, but you can also calculate the distance that you need in order to have a resonance at a certain frequency. Okay? And in this case, we have all the harmonics. So it's not just the odd ones, we have all of them. Why is this? It's because the two terminations are identical. Right? So either two nodes or two antinodes on both ends will give us all the harmonics. If they're not identical, if one side is open, the other one is closed, we will get only odd harmonics and half the fundamental frequency. Okay, so this will also come back in instrument acoustics. It's one of those things that needs a bit of time to settle in. So here is a practical example of axial mode calculation. So if you have a 6-meter distance between the walls, the first order axial mode will be 28 Hertz. Okay, so what does this mean? It's a mode, so you get a resonance there, right? So your room will boom at that frequency, so to speak. The other thing to observe here is indeed we have all the harmonics, and that's fairly straightforward. 2 times, 3 times that fundamental, 4 times, 5 times, and so on and so forth. Now the interesting thing here is, we're gonna get more into this later, is how do we figure out ideal room ratios? So you will see here is that if there is a simple ratio relationship between two dimensions of a room, what happens is that you will get overlapping peaks. And if you get overlapping peaks from different dimension resonances, then it's getting worse. Okay, then you get a bad room. Okay, and this is the bit of math here. So if your room length is 6 meters and the width is 5 meters, right, then the 5th mode of that dimension will correspond to the 6th mode of that dimension, right? And that means I'm going to have a problem. The interesting thing is that what we're looking there is actually typically the ratio of the dimensions. And here the ratio is 6/5, so a simple ratio. If it was an irrational number, if it was 1.3789542, right, a kind of a very long decimal, then there will be no overlaps in resonant modes. Okay, and there are a few different ways of deriving dimension ratios in order to avoid overlap of resonant modes. Okay, so those are your axial modes in this situation. Typically the kind of 80 Hertz area is almost problematic in almost all possible rooms. Ceiling reflections are typically totally unobstructed. I mean, unless you have some treatment there, and most rooms will boom quite a bit on the room height related mode, around, depending on the height obviously, but around there, 70, 80 Hertz. Okay, so this is just a set of axial modes, right? So only the modes that have to do with a single dimension in terms of resonance. And from here, we can also look into further 2 modes, right? So we have tangential modes. So these are the modes that rely on 2 sets of parallel walls, okay? So you can imagine it. I'm not sure if this is something you visualize easily, but you can imagine it as a plane. So here essentially I have 2 planes. I have this plane and I have that plane depicted, right? So I'm kind of looking at the sound which goes ceiling, side, floor, side, ceiling, side, floor in kind of one plane, right? So it does not touch all the walls, right? So it's kind of slightly more complex, and also the path length is larger, right? Fairly evident. If I have a larger path length, what will happen to the frequencies? The resonant frequencies?
They will arrive at different times.
Well, this is not so much about arrival. So you see, we have looked at situations with source and receiver, where we looked at the path difference. This is actually just the property of a resonant rectangle, really, right? So this is a two-dimensional thing. So in a sense, typically wherever you excite, wherever the source is, these will be prominent modes in the room. So from describing a source receiver relationship in relation to a reflector, now we look at what happens when there's multiple reflectors on top of each other. You actually get resonance. Okay? So from this single reflection scenario, what you want to remember, it gives you a comb filter, right? But this is actually starting to look a bit like a drum surface, right? I mean, in the end, we get a cavity, which is also even more complex. But at this stage, we're just looking at the properties of rooms. And in fact, what I've just said is not necessarily true, because it depends where you excite it along this line. It depends how well the resonance will build up. So there are some more details here. But in any case, axial modes, one-dimensional pathways, tangential modes, kind of surfaces that establish a cycle, a feedback path, so to speak. And we have oblique modes, where you actually touch all the walls. Okay, but all of these, the point is that they are circular paths, right? So this doesn't look like a circle, but it's just because it's bouncing back and forth. So why is this? Because if I have a wavefront which bounces back, it might as well arrive in phase with the next cycle. That's the point. So we have cyclical waves, right? They repeat. And if the delay is such that it creates constructive interference, then we get a resonant mode. Okay? And there's some really, I'm not sure how it's going to look like in instrument acoustics, but there's some really nice Java applets that do this, that physics professors created some time ago. That will show you kind of visually how this reflection builds up into a standing wave. And this is actually standing waves. Okay, so just a bit about that. It's quite important. I've heard some questions already. So how do you distinguish between standing wave and traveling wave? Well, it's kind of confusing because, it's a wave, so it's not standing, right? It's kind of contradictory term. But the point is that if you have a traveling wave, what you can imagine is an XLR microphone cable, and you do this, and it will kind of, the hump will travel forward, okay? And in a standing wave, what you imagine is a guitar string. So in the middle, you get the maximum excursion, and that's the standing concept there, because this peak does not move in this direction. Obviously, it moves up and down. But that's why it's a standing wave, because this peak remains localized like that. So in this case, these are all standing waves. Cool. Bit of math if you're interested, probably not, but you can calculate all the modes. We have, if you just type it into your search engine, room mode calculator, it will spit out quite a few options. You put in the 3 dimensions of the rooms, of your room, and then there's a variety of things it can give you, but typically your distribution of modes will be there. Some of them will immediately highlight overlapping modes. Here you kind of see it as a thicker line. These are the problematic things typically. So I guess we won't need to do this by hand at all. So let's look at some of many modes here. In fact, ordered by frequency. Okay, so there is the dimensions of the room that we're looking at. Okay, so the lowest frequency will have everything to do with the largest dimension in the room, right? And this is how we depict it. So we're looking at the first mode that relates to the x dimension and nothing relating to the other two dimensions. So you know this is an axial mode. Okay? If you have two non-zeros, here and here, sorry, two zeros, you will still be looking at axial modes. If you have a single zero, you're actually looking at tangential mode. Okay, so it means it's touching four surfaces. If you don't have a single zero, here's my first oblique mode. Okay, and then you can see if they are tricky, problematic overlaps. Actually, this seems quite decent. These two frequencies are a bit close together, but evidently as we progress, you will get softer modes and thereby less problematic. So the biggest problems are typically the lowest modes, and that's why you probably know it already. In small rooms, we have an issue with bass, right? So this is 4x4, a bit larger, 60 square meter, a bit larger than that. Actually, probably almost 20 here. And the lowest one is 36 hertz, right? So it kind of tells you you really want to push these modes as low as possible. So the best way to fix a room is to build a larger one, mostly. That's a rule of thumb. Okay, so if we plot all of these modal frequencies, we can estimate the modal density. You can find ways of quantifying this. You know, if you really want to compare two rooms with numbers, but it is also something that you can appreciate visually. And what you want for a good sounding room is good distribution of modes, right? You don't want them overlapping. You don't want large dips. You want them equally spaced, so to speak, and typically dense as well. Okay, so that's your modal density. Obviously, it will increase with frequency, right? As you've seen in the previous table. And it's actually one of the clues in terms of designing reverbs. I don't know if anyone has gotten into programming audio effects in this context. A very simple synthetic reverb will typically not have the increase of modal density with time. Okay, so if you just do multi-tap delay, right, it won't have an increase in modal density. How would you make it increase in modal density? Yeah, go ahead.
What do you mean by density in this context?
Well, density is the space between different modes.
So the correlation is the denser that this graph is, the smaller the room is?
No, the smaller the room, the more it's shifted into high frequencies.
Oh, okay.
Right? The density actually has to do with the ratio of the dimensions. So if you have a cube, right, 3 by 3 by 3, it is the worst possible thing because all the modes will align and they will give you huge peaks and a lot of space between the peaks. So you have low modal density, right?
How do you measure the density of a room?
It's not the density of the room. Density is a physical property in terms of material.
Yes,
It's not what we're discussing. We're discussing modal density,
Oh.
and we're not going to look into quantifying it. It's kind of over the top. But for us, it is kind of crucial to understand the relationship. So what you really want is room dimensions which are odd, right? So the worst situation is cube, 3 by 3 by 3. But if you have 3 by 3 by 1.5, it's still quite bad. You see, because 1.5 relates to 3 with a simple ratio, 1/2. So what you're trying to avoid is simple ratios, because you've seen, even if I have a ratio 5/6, at some stage there will be overlapping modes, which means less density and higher excursion and potentially unpleasant acoustic characteristic. Yes?
So on this chart here, we could have on the y-axis like the decibel levels.
Yeah. Yeah.
I see. And then the peaks will probably.
Yeah, it's actually a good comment. It highlights insufficiently well-designed graph. Axis should be labeled. Frequency level. Very good. Okay, so the interesting thing is that this coloration, which is produced by high peaks and low density, is something which is undesired in a control room, if you want a quality control room, but actually in recording rooms it might be very well desired. Okay, so we will talk about this distinction. As I said, for now we're just discussing the basic principles, and then we're gonna take these into practical context and thereby repeat them as well. So don't worry if things are not quite solid and didn't quite sink in yet.
Practical for the suite. So instead of measuring the room, we're just doing all the frequencies and measuring what the peaks are and working backwards from there. Or we could work backwards from there.
Yeah, exactly. So we will try and perform this whereby we have a prediction based on the room dimensions, we have a measurement, and then we look at the discrepancy. Okay? Typically, measurement is superior because that tells you what's going on. But predictions can be quite accurate as well. Okay, so here is another comparison of modal density. So the modes are depicted with dots here. At least we have a frequency label, level still not. Larger room, 8 by 7 by 5. Smaller room, 3 by 2 by 3. And you see the density difference. This one will sound much more natural. This one will be much more colored. So regardless of all the other parameters, all the possible treatments and everything else, you really want a large room.
Natural in colours here. We said how they sound.
Well, natural would imply that there is a correspondence with the spectral characteristic of the source and the spectral characteristic at the receiver. Right? So you kind of hear the naturalness of the source. Right? If you have a colored room, it means that certain frequencies will peak, the others will be dipped. So what you hear is more remote from the natural sound of the source. Okay? I mean, again, it's actually really fun if you think about it. When we describe sound, we only have metaphors and onomatopoeia. So I can say buzz, but actually that has to do with the word buzz sounding what I'm trying to describe. And all the other terms pretty much are borrowed from vision or tactile, soft. Loud is an interesting one, but I think etymologically loud is also borrowed. Would have to look this one up. Okay, thank you for your attention. Some tasks for next week. If you're interested, please go ahead. It's not
Can you
huge.
please show the code again? It didn't work for me. And
The attendance code.
yeah.
Okay. Here we go. So I'm going to share